What's up, guys? Welcome back to my channel, Wayne Cole. That's me. Today, just another quick video, and we're going to talk about Apple's private cloud compute, right? They've been in the news lately because recently Apple has paid Google about $1 billion for them to basically take, not even license, but like literally they're just handing over the model to Apple, I believe. Don't quote me on any of this. But I think they're just handing the model over to Apple in order for them to use on their own infrastructure and stuff. So we're just gonna dive in, and it got me interested because it just got me interested in looking into private cloud compute because that was actually my first time hearing about it was after the deal, and like I was like, well, what are they going to use it for? And I don't really use, like AI on my iPhone like at all, right? So I was just kind of just got me into looking. So we're just gonna dive into what private cloud compute is, and it's actually really interesting, and it caught my attention, and the technical aspects of it is like really crazy. So let's go ahead and dive in here. Let me switch my scene here. Okay. And by the way, I use Zen browser. So that's the browser that I use. I know it's probably not as well known, but it's really good. Scalar draw. Let me not do that. Okay, there we go. So let's go ahead and dive in here. So this is all the way back from 2024, June 10th. And let's go ahead and go through this article right quick. So private cloud compute. Oh, actually, I'll show you guys the other article for the Apple deal. So here, Apple nears deal to pay Google 1 billion annually. So it looks like this is some TechCrunch coming out of TechCrunch. Pay Google annually. So they're paying 1 billion annually. So it doesn't look like they're basically licensing out the model. So Apple is nearing a deal with Google that would see the iPhone maker pay the tech giant roughly $1 billion a year for a custom version of Google's Gemini AI model to power its overhaul of Siri, according to a new report from Bloomberg. And the thing about this, like, yeah, it's $1 billion, but I believe Google pays Apple like 12 billion, like in the double digits billion, right? For them to have Google be the default search engine. So it's really, you think about it, it's really not that much in like the grand scheme of things, especially considering how much Google is paying Apple to be the default search engine. And also, I think that Samsung did the same thing. I think Samsung phones uses a Gemini model in the Samsung ecosystem. So this is not this could be a whole nother video in and of itself. But we're starting to see a model where instead of you building your own foundational model, you're seeing Samsung almost lease out or license these foundational models from like from like these research labs, research companies, right? And in this case, Google, they're just licensing out what took them, billions of dollars in research, and they're just licensing it out, and they're just kind of using it on their own infrastructure. So this is pretty cool and a kind of a cool business model that we're seeing come up. And maybe companies don't actually have to invest money into the AI race as much as we think. So it's very interesting to see how this is going to shake out in the next like 5 to 10 years. So back to the article here. And this article is very technical. um some of it goes over my head, and I am my major is electrical and computer engineering, and a lot of this is even going over my head. Like, it goes, well, you'll see, but it goes really deep into the actual model of how they are going about protecting your privacy when you send in requests like through the system. So, oh, and also I want to say privacy and security is two different things. Like, and it even dives into it. You'll kind of see how it says if somebody were to get a hold of the data, They still couldn't de-anonymize it to where they could attach you to the request, right? So if I know Apple gets a lot of flack, and I'm just really yapping right now, but I know Apple gets a lot of flack when it comes to privacy and like data security and stuff like this, and like the whole ecosystem trap and like entrapment and all that kind of good stuff. And I'm definitely a shield. I have a Mac, I have an iPhone, I have an Apple Watch. That's pretty much the extent of it. But Apple is pretty much unmatched when it comes to protecting their users' privacy. And I don't think they get enough credit for that. But let's dive back into the private cloud compute. So, here is a new frontier for AI privacy in the cloud. So, right, so it's written by Apple Security Engineering and Architecture. So it looks like it's written basically by the whole team, so writers and stuff. So here we go. So Apple Intelligence is a personal intelligence system that brings powerful generative models to the iPhone, iPad, and Mac. For advanced features that need to reason over complex data with larger foundation models, we created Private Cloud Compute, PCC, a groundbreaking cloud intelligence system designed specifically for private AI processing. For the first time ever, private cloud compute extends the industry leading security and privacy of Apple devices into the cloud, making sure that personal user data sent to PCC isn't accessible to anyone other than the user, not even to Apple. And it's built with custom Apple silicon and a hardened operating system. That's this right here is pretty cool. We're going to dive into that later on in the article. So, hardened operating system designed for privacy. We believe PCC is the most advanced security architecture ever deployed for cloud AI compute at scale. So here's just talking about Apple has long championed on device processing, right? So just basically talking about how Apple likes to do stuff on device. Data only exists on the user devices. For the most sensitive data, we believe end-to-end encryption, right? So like the same thing, like with iMessage, end-to-end encryption. For cloud services where end-to-end encryption is not appropriate, right? We strive to process user data I can never say this word, infirmally. This is one of those tough words to say for me. I don't know. I'm a little bit dyslexic. Or under, even though I'm like a huge reader, or under uncorrelated randomized identifiers that obscure the user's identity. I think it's really secure and private AI processing in the cloud poses a formidable new challenge, right? So powerful AI hardware in the data center can fulfill a user's request with large, complex machine learning models, but it requires unencrypted access to the user's requests and accompanying personal data, right? So your IP address, user information, data, hardware that you sent it for, all that kind of stuff, right? So here that precludes the use of end-to-end encryption. So cloud AI applications have to date employed traditional approaches to cloud security. Such approaches present a few key challenges. So here are the challenges. So cloud AI security and privacy guarantees are difficult to verify and enforce. It's difficult to provide runtime transparency for AI in the cloud. It's challenging for cloud AI environments to enforce strong limits to privileged access. So, when on device computation with Apple devices such as iPhone or Mac is possible, the security and privacy advantages are clear. Users can control their own devices. Researchers can inspect both the hardware and the software. They can do the runtime transparency. They can make sure that it's cryptographically assured through the secure boot. And Apple retains no privileged access. So you get all that. So, however, the process more sophisticated requests the however, to process more sophisticated requests, Apple Intelligence needs to be able to enlist help from larger, more complex models in the cloud, right? Because you can't run a Gemini model on an iPhone, just not possible yet. So for these cloud requests to live up to the security and privacy guarantees that our users expect from our devices, the traditional cloud service security model isn't a viable starting point. Instead, we need to bring our industry leading device security model for the first time ever to the cloud. So Very, very interesting in how they're upholding their promise of privacy. So the rest of the post is an initial technical overview of the private cloud compute, followed by a deep dive after PCC becomes available in beta. And they actually have a code base that they release for security researchers. And we know researchers will have many detailed questions, and we look forward to answering them in any of our follow up posts. So designing private cloud compute. We set out to build private cloud compute with a set of core requirements. First is stateless computation on personal user data, enforceable guarantees, no privileged runtime access, non-targetability, verifiable transparency. So this is an extraordinary set of requirements and one that we believe represents a general leap over any traditional cloud service security model. So now, I think I'm getting sick now too. But here we go. So introducing private cloud compute nodes, the root of trust for private cloud compute in our compute nodes. So they have a custom built server hardware that brings the power and security of Apple Silicon to the data center with the same hardware security technology using iPhone, including the secure enclave and secure boot. So they basically paired the hardware with a new operating system, and it's a hardened subset of the foundations of iOS and macOS, but it's tailored to support LLM inference workloads while presenting an extremely narrow attack surface. So basically, they just created a new operating system that's a subset of iOS and macOS, but it's just tailored to LLM inference workloads. So it's pretty interesting. And apparently, it allowed them to take advantage of the code signing and the sandboxing. So it's pretty cool. So on top of this foundation, they also built a custom set of cloud extensions with privacy in mind. So they basically excluded components that are traditionally critical to data center administration. So they basically have no remote shell. They removed system introspection and observability tools. So basically, it took out logging and all that kind of good stuff. We replaced those general purpose software components with components that are purpose built to deterministically provide only a small restricted set of operational metrics to the site reliability staff. And finally, we use Swift on server to build. They use Swift to build. Well, of course, they use Swift to build a new machine learning stack specifically for hosting our cloud-based foundation model. So let's take another look at the core requirements and what they built to achieve them. So in order for them to get stateless computation and enforceable guarantees, they basically designed to make certain about the way it handles user. We designed properly make sense. So basically, a user's device sends data to PCC for the sole exclusive purpose of fulfilling the user inference request. So PCC uses that data only to perform the operations requested by the user, and they don't do anything else with it. And the user data stays on the PCC nodes that are processing the request only until the response is returned. So once you send a response, well, you send a request to one of the PCC nodes, it only keeps the information about the request as long as like basically as long as you get the request, you get the response back to your actual phone. So as soon as you get the response back, apparently it deletes it. It deletes the user's data after fulfilling the request, and no user data is retained in any form after the response is returned. And the user data is never available to Apple, even to staff with administrative access to the production service or hardware, right? So when Apple Intelligence needs to draw on private cloud compute, it constructs a request. It consists of a prompt plus the desired model and inferencing parameters that will serve as an input to the cloud model. So basically, your standard, like how you would normally do it if you were using Python and you were using a kind of open AI, like kind of standard API requests. the PCC client on the user's device then encrypts this request directly to the public key. So here's where it kind of gets cool. So basically, the PCC client, which is basically your phone, on the user's device, then encrypts this request directly to the public keys of the PCC nodes that it has first confirmed are valid and cryptographically certified. So this provides end-to-end encryption from the user's device to the validated PCC nodes, ensuring the request cannot be accessed in transit by anything outside those highly protected PCC nodes. And it support data center services such as load balancers, and privacy gateways. Run outside this trust boundary and do not have the keys required to decrypt the user's request. Interesting. So supporting data center services such as the load balancers and the privacy gateways run outside of the trust boundary. Okay, I see. So basically, any load balancer or privacy gateway, they can't see what the request is because it's been already cryptographically signed by the PCC node and the actual client itself. So next, we must protect the integrity of the PCC node and prevent any tampering with the keys used by PCC to decrypt user requests. So the system uses secure boot and code signing for an enforceable guarantee that only authorized and cryptographically measured code is executable on the node, right? So all code that can run on the node must be part of a trust cache that has been signed by Apple, approved for that specific PCC node, and loaded by the secure enclave such that it cannot be changed or amended at runtime. This also ensures that the just-in-time mappings cannot be created, preventing compilation or injection of new code at runtime. Additionally, code and model assets use the same integrity protection that powers the signed system volume. So finally, the secure enclave provides an enforceable guarantee that the keys are used to decrypt requests cannot be duplicated or extracted. So you see how they just went all in, and man, I wonder how many engineering hours I went into this. Pretty insane. So the private cloud compute software stack is designed to ensure that user data is not leaked outside the trust boundary. And the trust boundary is basically their hardware, like everything that Apple has control over, all the way up from the actual physical devices itself, the actual physical hardware, or retained once a request is complete, even in the presence of implementation errors. So the secure enclave randomizes the data, volumes, encryption keys on every reboot. So every time one of them reboots, it literally randomizes the data, volumes, encryption keys on every reboot and does not persist these random keys, ensuring that data written to the volume cannot be retained across a reboot. So in other words, there is an enforceable guarantee that the data volume is cryptographically erased every time the PCC node secure enclave processor reboots. Pretty insane. So the inference process on the PCC node deletes data associated with the request upon completion, and the address spaces that are used to handle the user data are periodically recycled to limit the impact of any data that may have been unexpectedly retained in memory. It's pretty crazy. So finally, for our enforceable guarantees to be meaningful, we also need to protect against any exploitation that could bypass these guarantees. So technologies such as pointer authentication codes and sandboxing act to resist such exploitation and limit an attacker's horizontal movement within the PCC node. So if they were to gain access to one of the nodes, they couldn't gain access to a node and then hop to another node and hop to whatever, they just move horizontally within wherever level of privilege maybe they got access to. So the inference control and dispatch layers are written in Swift, and they actually have the Swift code on GitHub for security researchers and stuff like that. And so ensuring memory safety. I've never used Swift before, so I don't know how you guys could tell me if is Swift memory safe like Rust or something. And use separate address spaces to isolate initial processing of request. This combination of memory safety and the principle of least privilege removes entire classes of attacks on the inference stack itself and limits the level of control and capability that a successful attack can obtain. So here we design private cloud compute to ensure that privileged access doesn't allow anyone to bypass our stateless computation guarantees, which is basically what we just went over. So like we said earlier, they didn't include a remote shell, so like you literally probably can't SSH, right? They removed any interactive debugging. Our code sign presents any mechanisms for loading additional code. Open-ended access would provide, but this sort of open-ended access will provide a broad attack surface to subvert some security or privacy, also not including the shell, remote or otherwise. PCC nodes cannot enable developer mode at all, and they don't include the tools needed by the debugging workflows. So basically, you literally just can't see inside the system, or you can't interact with the system, basically. So next, or at least it's significantly limited. So next, we built like you know how you could usually SSH into a server. You basically just can't do that, but way more complex. Next, we built the systems of observability and management tooling with privacy safeguards. So they do have some system observability and they have management tooling, but they built their own stack basically. So they're designed to prevent user data from being exposed. So like for example, they don't even include a general purpose logging mechanism. Instead, they only use pre-specified structured and audited logs and metrics can leave the node. Wait. So instead, only pre-specified structured and audited logs and metrics can leave the node. I see. And multiple independent layers of review help prevent user data from accidentally being exposed through these mechanisms. So basically, they built in only pre-specified data can actually leave out of the node, basically. So it's probably hard, like programmed in or however they do it. I'm not an expert. I'm not that low level. But basically that's the only data that can escape from one of the nodes is basically what they have already predefined that can actually leave. So then they have mechanisms from anything accidentally leaking through these mechanisms. And they have traditional cloud AI services, such mechanisms might allow someone with privilege to actually observe or collect user data, which, they don't have any of these traditional mechanisms. So it will be virtually impossible. So these techniques can provide enforceable guarantees that specifically designated code has access to user data, and they cannot leak outside the PCC node during sys administration. So here, this is where it gets pretty crazy. So the non-targetability. Our threat model for private cloud compute includes an attacker with physical access to a compute node and a high level of sophistication. That is, an attacker who has the resources and expertise to subvert some of the hardware security properties of the system and potentially extract data that is being actively processed by a compute node. And they basically defend against this type of attack. So if somebody literally got access to a compute node, they have these protections. So looks like, what do they do? We supplement the built-in protections of Apple Silicon with a hardened supply chain for the PCC hardware so that performing a hardware attack at scale will be both prohibitively expensive and likely to be discovered. So we limit the impact of small-scale attacks by ensuring that they cannot be used to target the data of a specified user. So basically, this is like the anonymization of the data, right? So like If it limits a small scale test by sharing that it cannot be used. So basically, they anonymize your data on if it did so happen to leak, it couldn't really get traced back to you. Um, so here it says this is one of the big things, when these companies actually, and the reason why I'm covering this, right, is because when companies talk about privacy, it's usually just surface level. It's usually just optics, it's PR, it's to get a good story, it's almost just selling customers a dream. But I think what people don't really know about Apple is like they actually do this for real. Like here it says private cloud compute hardware. The security, right? It starts at manufacturing. So where we inventory and perform high resolution imaging of the components of the PCC node before each server is sealed and its tampered switch is activated. So when they arrive in the data center, we perform extensive revalidation before our servers are allowed to be be provisioned for PCC. So this process involves multiple Apple teams that cross-check data from independent sources, and the process is further monitored by third-party observers not affiliated with Apple. So at the end, a certificate is issued for keys rooted in the secure enclave universal ID, I'm guessing UID, for each PCC node. The user's device will not send data to any PCC nodes if it cannot validate the certificates. So these processes broadly protect hardware from compromise, and to guard against smaller, more sophisticated attacks that might otherwise avoid detection. Private cloud compute uses an approach we call target, that they call target diffusion, right? So to ensure requests cannot be routed to specific nodes based on the user or their content. So let's say you was in a specific region or you had a specific type of request, I guess, and it was maybe cat. I don't know what they mean by or their content. So maybe like cached or something like that. I don't know. Target diffusion starts with the request metadata, which leaves out any personally identifying information about the source device or the user and includes only limited contextual data without the request that's required to enable routing to the appropriate model. So this metadata is the only part of the user's request that is available to load balancers and other data center components running outside of PCC trust boundary. Interesting. So the metadata also includes a single use credential based on RSA blind signatures to authorize valid requests without tying them to a specific user. Interesting. So additionally, PCC requests go through an OHTTP relay operated by a third party, which hides the device's source IP address before the request ever reaches the PCC hardware. So this is getting pretty insane, right? So it does that before you get to their infrastructure. This prevents an attacker from using the IP address to identify requests or associate them with a individual. It also means that an attacker will have to compromise both the third-party relay and their load balancer to steer traffic based on the source IP address. So very, very interesting. And the user devices encrypt requests only for a subset. So it gets even more crazier. So basically, a user's devices encrypts the requests. All right, so we talked about that earlier, and it only does it for a subset of the PCC nodes, right? So you can't go to every PCC node just because your device has verified and that it can actually send a request. So rather than the PCC service as a whole, when asked by a user device, the load balancer returns only a subset of the PCC nodes that are most likely to be ready to process the user's inference request. So, however, as the load balancer has no identifying information about the user or device for which it's choosing nodes, it cannot bias the set for targeted users. By limiting the PCC nodes that can decrypt each request in this way, we ensure that if a single node were ever to be compromised, it would not be able to decrypt more than a small portion of incoming requests. So finally, the selection of PCC nodes by the load balancer is statistically auditable to protect against a highly sophisticated attack, where the attacker compromises the PCC node as well as attains complete control of the PCC load balancer. And basically, it just goes in and it's talking about verifiable transparency. This is mostly just for security researchers. So they uploaded their code to GitHub, and you can find it um, on GitHub as well. See if we can find it real quick. Uh, what? Let's see. So here we have the private cloud compute code. This is their source code. Source code. I can't even talk. This is the source code here. I have mine. I have a star because I actually was looking at this earlier. But here you can just kind of see the private cloud compute. Looks like it was like it was updated 2 weeks ago. Yep, October 24, and this obviously the deal happened, right? So this is very recent. Updated October 31st. So very recent code changes, very recent commits. But yeah, so it is. I think it's about almost a line in Swift. Like I don't know anything about Swift, but I was looking at this code earlier and it's pretty cool. But yeah, 85% Swift, some C, Objective C, but pretty much goes to territory because it's Swift. So, but yeah, that's mostly that. But yeah, I just wanted to talk about that, man, because I just thought it was pretty cool, and I don't think a lot of people know about PCC. So just kind of running you guys through it. But basically, everything is verifiable, right? Like they built it to where security researchers and the public can actually go in and verify that this is actually what it says that it is. And I think that that's pretty cool. I don't think a lot of companies do that. And if they do it, it's usually not from these huge companies, right? You won't see Google doing this. You won't see big companies doing this type of stuff. And I just find it very interesting just because I like doing I like servers. I like that kind of things. Like this is very much interesting me. So hopefully you got some interest from it too, and you got some new knowledge, and you just can go and you can look at the code and you can reread this article. I believe that they made an update to this article, so you can go and read that. It's probably up on their site. So just look at security.apple.com and probably find the more recent one. But yeah, man, this is pretty interesting. So appreciate you guys watching. Catch you guys on the flip side. Don't forget to be better than yesterday. Peace.